Hello everyone, thank you for joining me today. My name is Sailesh Dwivedi. I'm responsible for product management and cloud engineering for Oracle Database Sharding. We'll do a quick overview of sharding and see how it helps internet scale applications. We'll see how it works under the hood, and we'll discuss some of the new features we introduced in 21C. Here is an example of a truly internet scale application. Such application typically tends to have very large data volume, big user population. They require extreme low latencies. At times, they are global in nature, so they also need to comply with country-specific or region-specific data sovereignty or data residency requirement. Oracle BlueKai is a part of our Oracle Fusion application suite. They've been using Oracle Database Sharding for a while now. And if you look at some of the numbers, they have about 2.5 petabytes of data. And they have many tables. One of the biggest tables they have has 22 billion rows. They have been able to achieve extreme low latencies, 1.6 millisecond read latency and 2.5 millisecond write latencies. And these are end-to-end latency where the request hits the load balancer, the web server, the application server, database, and back. Now, each of these API call has about 125 KB of payload, and they are having about 30 billion API calls per day. It also requires extremely high throughput data ingest. They are generating redo at 180 terabytes per hour. This application with Oracle Database Sharding is running in Oracle Cloud. We have about 52 compute instances. Each of these compute instances has over 50 cores. So we have a single database with the 2,704 cores and 38,740 gigabytes of memory. I did not include the replicas in these numbers. So we have equal amount of data as well as nodes for replicas. So sharding has been used to scale internet scale applications. What Oracle Database Sharding is, just like other sharding technologies, is horizontal partitioning of data across independent nodes. It uses a shared nothing architecture, and it also enables massive parallel processing. So in this picture, to the right side, I'm showing 3 shards which are deployed on 3 different machines. There are 3 different compute instances. So let's say we have server 1, server 2, and server 3. Each of these server has a regular Oracle database instance. We call it shard. So we have shard 1, shard 2, and shard 3. And let's assume this application had one table called table 1. Of course, we can have many tables and schemas, and that is all supported with sharding, but just for the sake of discussion, let's say we had one table. Now, if this table had, say, 300 rows, then what we do is we partition the data. We say put row 1 to 100 on shard number 1, which is on machine 1, 101 to 200 on shard 2, and 201 to 300 on shard 3. So this way, each shard holds a subset of data. There is no single point of failure. It's all protected with a variety of high availability technologies we have with the Oracle database. As I said, it's a shared nothing architecture, so it does not require any specialized hardware or software. Doesn't need a shared storage, NAS, or a SAN storage device. No need for any specialized network cards, host bus adapters, or any kind of software. Now, when application connects or queries the data, our drivers, whether our like Java driver, C, C++, Python, Go, .NET, all of those drivers have been enhanced to understand sharding. So the application automatically gets connected to the right shard where the data is residing. And from an application point of view, it looks like a single database. Additionally, we also support massive parallel processing. So if you have queries where we need data from more than one shard, such queries go to a sharding coordinator, which in turn pushes those queries to all the shards in parallel. Each shard executes that query on subset of data it has, returns results back to the coordinator, which takes all the results and then sends it back to the application. So sharding, from an application point of view, presents a single logical database which is spread across these multiple shards. From an operations point of view, it's a single logical database. We have a centralized administrative server from where we can execute our DDLs and other management operations. So what are the benefits of sharding? Well, number one is linear scalability. What that means is that if we have more data or more transaction volume, we can just horizontally scale by adding more nodes. Additionally, when we want to shrink the number of nodes, we can do so without losing data. So, for example, if there is a holiday season coming, you want to add more capacity, and then when the season is over, you want to take away that capacity. We can do all of that without losing any data, without any downtime. The second big reason why customers use sharding is for extreme availability. As I said before, there is no single point of failure in this architecture, but in case there is an outage, and even for that outage, if there is a small blip or a brownout, that is contained to just one of these shards. So that reduces the blast radius of an outage and improves the availability. The third big reason why customers use sharding is for geographic data distribution. So, as I said before, there are a lot of country-specific, region-specific requirements. For example, US data should stay within the boundaries, geographical boundaries of United States. European Union data should stay in EU. Asia-Pacific data could be country-specific and needs to stay there. Now, with sharding, we can deploy these shards across the globe in many regions. And from an application point of view, it seems like a single logical database. As I said before, from an operation point of view, it is a single logical database. Application automatically gets routed to the right node where the data is residing, honoring the data residency requirements. Oracle database is a converged database. That means we can store relational data, documents, JSON data, graph, spatial, text, all different types of data in a single database. And we can use that database for online transaction processing, analytics, and other use cases. Sharding supports all of these data types, which means we can have a single platform to store all of our structured as well as unstructured data, which we can scale. Here are some of the use cases for customers who are using Oracle Database Sharding. We also talked to them and asked them what other products did they consider and why did they choose Oracle Database Sharding. So there are applications which are internet scale real-time online transaction processing application, like mobile to mobile payment application, marketing application, some real-time billing applications, financial stock trading applications, so on and so forth. So these are applications which require extreme low latencies and absolute data consistency. And of course, they considered many other NoSQL products and they chose to use Oracle Sharding. Global database, data sovereignty, things like healthcare, medical record, payment card industry, so on and so forth. Those kind of applications also use sharding for data sovereignty use case. Oracle database has first-class support for text data, log data, so use cases like log analytics, text store can also be used with sharding, and that's what these applications are using it for. Applications like which are using Oracle database for metric store, time series data, Internet of Things, application performance monitoring, all of them store data in Oracle database with sharding and be able to scale it. Other use cases like machine learning, where you run your algorithm for a very big data set inside the database where the data resides, helps with the model training as well as scoring within the database. And then, of course, big data analytics, where we have massive data volume spread across multiple nodes, and we use massive parallel processing capabilities of Oracle database to serve such requests. Sharding provides many benefits over a lot of NoSQL products which we just saw customers considered. Number one, it scales better than a lot of NoSQL products out there in the market. It supports Converge database, and you can continue to use the same SQL as well as the programmatic interfaces that many of your applications already use with the same Oracle database. It provides strict data consistency, zero data loss, ACID transactions, things like two-phase commit, complex joins, triggers, stored procedures, all of that which is there in Oracle database can be used with sharding and be able to scale that to those numbers. Because of support of these sets of features are there in database, then the schema resides in the database. Instead, with many other NoSQL technologies, application developers end up implementing such functionality inside their application because applications do need these capabilities. Oracle database also has many other great features which are all available with sharding, things like in-memory, columnar, hybrid columnar compression, partitioning, sub-partitioning, advanced compression, secondary indices, security capabilities, replication capabilities, parallel query, and be able to run on Exadata. All of these features and capabilities are available with Oracle database sharding. And of course, you can leverage your in-house DBA skill set and programming skill set. Many of you are already running Oracle database, know how to provision, patch, upgrade, and code against an Oracle database. So you can preserve all of that investment in terms of skill set and use sharding to scale your applications. And many times customers don't realize that they probably already own sharding. It is included as a part of our enterprise edition license, and pretty much all the feature set is available for you to use. So let's see how it works. So here's a sample schema here. Let's say we have an e-commerce or like an online ordering application. And let's say we have 3 tables in this application: customer, order, and line item. And there's another table, let's call product, which stores all the product catalog data. So customer, order, and line item table, we can actually shard it. And let's say we sharded it. And that what that means is that we basically partition the data for these set of tables. These set of tables, which we also call as a table family, are a group of tables which are sharded by same sharding key. A sharding key is nothing but just like any other primary key, and it could be a single column or multi-column as needed. So in this example, let's say we have 3 customers, Mary, John, and Peter. Now, Mary's data is shown in pink, Peter's data is in orange, and John's data is in orange, and Peter's data is in gray. So what we do is that for a given sharding key, let's here in this case customer ID for Mary 123, all of Mary's data is stored. We co-locate and store it on a given shard. In this case, shard number 1. All of John's data, which is in orange, is stored on shard number 2, and all of Peter's data is stored on shard number 3. The reason we partition and co-locate the data in this manner is to ensure that we are able to satisfy most of the joins locally. That means we don't want these shards to talk to each other at the runtime, and that way we get extreme performance. Now, let's say we also have data which is not specific to any customer and does not need sharding. So, for example, a good example could be something like a product catalog, set of products which any customer could potentially buy. So we call this such data, we call as a duplicate table data or a reference table data, and this data is copied on all shards. So we make a copy of this data and make it available on one shard. Now I can run queries against sharded table and duplicate tables and do joins across them. So for example, if I want to find all the products which Mary bought, now that query can be satisfied on shard number 1. Additionally, if there are queries which require data from multiple shards, then as I said before, we have a multi-shard query coordinator. The request goes to the coordinator. Coordinator pushes that query in parallel on all 3 shards and gets the data. And then additionally, if there is any need to do a group by or even join across the data coming from two shards. Coordinator does that, and the results are sent back to the client application. We have a concept of chunk, and what you can think of chunk is a slice of data. It's basically a group of related partition of the data for a given sharding key. So in this example, let's say we had a chunk called chunk number 1. It has data for the sharding key from 1 to 1 million. In this case, all the customers from 1 to 1 million, their order and line items. Chunk is just a logical concept, and there is no limitation on the number of chunks we can have in a sharded table. It's also important because this is our unit of data movement. We talked about being able to rebalance the data, elasticity, and when we move data, we move in the units of chunks. This is what a shard looks like under the hood. So a shard has a bunch of chunks which have the data for the sharded table, and then the data for the duplicate table. So in this case, chunk number 1 has customers 1 to 1 million, their order and line item. Chunk number 120 has customer 5 million to 6 million, their order and line item. And then of course we have the data for the duplicate table. Now when the application connects to a sharded database, it doesn't need to connect directly to the shards. That means applications don't have to have host port information of all the shards. We support up to 1000 shards. That's also a logical limit in a sharded database. What we have is another component called shard director. So application connects to the shard director, and based on the query patterns, if there is a sharding key available, the shard director routes that query directly to the shard where the data resides. We call this as a direct routing. Additionally, if there is no sharding key available at the time of query, shard director automatically routes the request to the multi-shard query coordinator, which in turn pushes the query to the right set of shards and gets the data and returns it back to the client. We call this as proxy routing, where we are going through a proxy instead of directly going to a shard. All this logic and understanding of sharding is implemented in our different language drivers like JDBC, Java, C, C++, Python, Go, .NET. All these drivers have been enhanced to understand sharding and are able to do the request writing the way I explained. We also have a component called shard catalog. That is our metadata store. That is where we store all the information about all the shards in a sharded database, what data is residing on which shards, the schema definitions, as well as the gold image of the duplicate table data. This is also the administrative server. What that means is that if you want to create any sharded object, you don't have to log into all the different shards. You go to this shard catalog, and from there you issue your DDLs. Additionally, shard catalog also acts as the multi-shard coordinator, and that itself is a horizontally scalable component, which means we can add more nodes to scale the query coordinator. If you have a lot of multi-shard queries, we can just horizontally scale multi-shard query coordinator by adding more of them. There is no single point of failure in this configuration. Each shard can be protected by a data guard, golden gate in a shared nothing architecture. And if you are using Oracle Database RAC, then you can use that as well, where each shard could be, say, a 2-node RAC cluster. Some of our biggest deployments actually use such a topology where they have each shard is a 2-node RAC cluster, so that way they can have the benefit of sharding by horizontally scaling the data as well as transactions, and have a protection from a node failure, instant protection from a node failure. Now, how can we partition the data? What are the different schemes and methods we allow for partitioning the data or sharding the data? So number one is system managed sharding. Here, what we do is under the hood, we place the data using a consistent hash algorithm. So what we can do is we can give a pool of shards, and the data placement on those shards is automatically handled by the system. Additionally, when we add shards or remove shards, we have automation to rebalance the data and redistribute it evenly. The benefit of system managed sharding is that you don't have to worry about fine-grained data placement rules, as well as be able to benefit from automated redistribution of data. The second sharding method is user-defined sharding. Here we can place the data by a range or list. Range is the example I was using earlier, where say customer 1 to 100's data is on shard number 100 and 1 to 200 is on shard 2, so on and so forth. List example could be something like if a customer's state of residence in United States is on the east coast of United States, like Florida, New York, New Jersey, place them in a data center which is on the east coast like Ashburn. Or if customer's state of residence is on west coast of United States, like California, Oregon, Arizona, put them in a Phoenix data center which is on the west coast of the United States. Additionally, we support something we call as a composite sharding, which is a very unique differentiator with Oracle database sharding. What this is a combination of the two aforementioned sharding techniques. By that we mean is that we can use two schemes to shard the data, which allows us to have two levels of sharding by different sharding method, as well as we can use a different sharding key for each of the two levels. Now that is what enables our global database use case. So for example, I have a global application which needs a database where for data sovereignty reasons, the data needs to reside in a specific geographic location. So with the composite sharding, I can create such a global database. For example, I can say that all the data for North America, continent of North America, is made available in shards in, say, Phoenix in United States. All the data for European Union customers needs to be deployed in Frankfurt. All the data for Asia Pacific customers needs to be deployed in say Tokyo. For data residency or user proximity, device proximity reasons. In Phoenix in US, I have 5 shards, and I don't want to micromanage the data placement, so spread it evenly. Likewise, I have 3 shards in Frankfurt and 7 shards in Tokyo. So what we can do is we can use the user-defined sharding, which is list-based, where if the customer's country of residence is United States, Canada, Mexico, put their data in a Phoenix data center. If a customer's country of residence is France, Belgium, Germany, put them in Frankfurt data center, so on and so forth. So that's what enables geographic data distribution as well as gives us the linear scalability. Now, as I said before, we also provide elasticity, which means we can add shards and remove shards completely. This is a complete online operation without incurring any downtime. Now, the unit of resharding is the chunks. And in this example, what I'm showing is that we can add a new shard and the system can automatically rebalance our data. So chunk number 4, 8, and 12 could be moved automatically to, say, the shard number 4, which is the newly added shard. Or customers can control the movement of chunks at their time of choosing. This is a completely online operation and doesn't require any downtime at all. Likewise, we can move all the data either automatically or administrators can trigger that to say the shard number 1, 2, and 3, and empty shard number 4, and then decommission it if you want. Under the hood, we use RMAN incremental backups and transportable table spaces. Enterprise Manager 13 version has very rich support for sharding, for visualization, alerts, notification, and many other use cases. In this screenshot, I'm showing that we have 2 regions, multiple shard groups, 30 shards, some of them are primary, 15 of them are primary, 15 standbys, the chunks and the services. We can look into the entire sharded database holistically as one logical database, as well as drill down into a specific shard or a specific chunk. We can see which shards are running hot, and within a shard which chunks are hot, and by hot I mean have a lot of queries or are going in the data size, and probably needs additional capacity. We can use sharding in conjunction with Exadata. Sharding on Exadata benefits from all the great capabilities of Exadata, like storage cell, query offloading, hybrid columnar compression, in-memory, as well as we can store all different types of data in Exadata and shard it and use that as a single data platform for our structured and unstructured data. Let's take a look at some of the new features we introduced in database version 21C. First feature is automatic identification of sharding key for Java EE or Java applications. What we do here is that we look at the query's bind variables, and we know which of the variables represent the sharding key, and we automatically extract the sharding key and route the application request either to the right shard or to the query coordinator, multi-shard query coordinator, if the query is going to be a multi-shard query. So what that helps us is that we can shard the data, DBS can shard the data on the database side, and there is no need to change application code. The existing application code will automatically work with sharding. Another feature we introduced is deployment automation. So we have a component or a tool called Sharding Advisor. So if you have an existing Oracle database and you want to use sharding with that, then you can run this tool and it gives you advice on what table should be sharded table, what tables should be duplicate tables, and what are the good candidates of sharding key. We do this by looking at the existing product databases query patterns, historical data. We look at AWR data, a bunch of $V tables, and then based on the usage patterns, such recommendations are provided. Additionally, we have a lot of deployment automation. We have released a Kubernetes operator for sharding. We have Terraform automation. We have Ansible automation. We have support for Docker containers. Sharding is available in Oracle Cloud as well through Marketplace offering. The Kubernetes operator and other automation mechanisms support for initial setup, add nodes, remove node, in case of any issue, be able to pause, resume, clean up, and all of this is available on premises as well as in cloud. We also added functionality around centralized backup and recovery with sharding. What that means is that you can go to one of our tools or the GDSCTL, which is the tool with which you do administrative operation on sharded database, and from there you can run a single command to back up all the shards. What we do under the hood is that we force an SCN across all the shards, and that allows us to take a consistent backup for your entire sharded database. Subsequently, we can recover either a given shard or entire sharded database. For example, if I want running some testing and I want to clone my production environment and then run my destructive testing on that and then rewind it back to the state it was, I could do a recovery which recovers all my shard. Or if there is an outage on a given shard, I could go and recover just one shard in the production outage scenario. We support variety of backup locations, including disk, and then shortly we'll be releasing object store and ZDL array as well. Another feature we introduced based on some customer ask was being able to upgrade databases using a shard replacement technique. This applies to minor patches, release updates, as well as major updates. For example, going from 19C to 21C database, what we could do is in an existing sharded database, we can add some new shards which are of newer version 21C, and we can move chunks from the older version to the newer version. And when the old version shard is empty, we can decommission that shard, and that way all my data has migrated to 21C. We also support persistent memory. So persistent memory allows us to store data as it says in the Intel Optane PMEM chip. Now with that, it is a non-volatile store, but it gives you the same performance, almost the same performance as DRAM. So now if all my data is stored in persistent memory, I almost get a database performance which is comparable to DRAM. But each host can only have so much persistent memory. If I have a 100 terabyte database and suppose I can have 20 terabytes of persistent memory on a given node, I can scale by adding more nodes and shard it so that each node has 20 terabytes, and I can have 5 shards which can allow me to have, say, a big 100 terabyte database, all being served from persistent memory. We also published a live lab, and it's a part of our live lab offering. So I'll encourage you to go and take a look at this live lab. Here you will get a sharded environment set up. We have an application which is already deployed. You can look at, you have full access to these nodes. You have OS access, root access to OS. You have sys access to the database. You can look at how this sharded database was created, how the schemas were created, as well as look at the application code which is deployed in a node.js container. So all of this is available to you. You can go and try this out lab for free and familiarize yourself with sharding concepts and see sharding in action. In summary, sharding enables hyperscale globally distributed databases. It can be used for structured and unstructured data. It can be used for online transaction processing analytic workloads, and it's included as a part of Database Enterprise Edition. More likely than not, you already have it, so please use it. Here are some of the resources, and thank you again for your time.